Hi there, my name is Heinrich and today I'd like to talk to you about galvanic cells. So here we have an example of a galvanic cell. So here we've got zinc and copper reacting in order to form a zinc ion and a copper solid. So the first thing we have there at the top is called the cell reaction, right? And that's the redox reaction that describes what's happening in the cell. Right, so let's see. We have the zinc half cell, right? And in the zinc half cell, the zinc half reaction happens. So we have zinc forming zinc ions, right? Where it lost electrons. So in the zinc half cell, we have oxidation occurring. And in the zinc half cell, there is a liquid. And that liquid is called an electrolyte. And in that electrolyte, there are ions. Right? So the reason we use a liquid is because when we put ions in a liquid, they can move freely and that allows it to conduct electricity. So we need an electrolyte, so a solution with ions in it, in order to conduct electricity. Then we've got the copper half cell, and in the copper half cell we have the copper half reaction where we have copper that's gaining electrons in a copper ion that's gaining electrons in order to form copper, right? So that is reduction. Reduction is the gain of electrons. So in that cell, we've got a copper sulfate solution so that we have copper ions and sulfate ions in that solution. Right, so let's see how the cell works. So there I've got a representation of a zinc atom that is on the zinc electrode, and you can see a copper 2+ ion in the copper half cell. Right, so oxidation occurs at the zinc anode, right? So oxidation happens at the anode, which means there is a loss of electrons. So the zinc loses its electrons and the electrons goes through the circuit towards the copper electrode. Right, so that zinc atom turns into a zinc 2+ ion and that ion moves into the solution in the zinc half cell. The copper 2+ ion goes to the electrons that are now on that electrode and it bonds with them in order to form a copper atom. And in that way we have copper ions moving out of the solution and coating that copper electrode. Then we've got this thing called a salt bridge. Now the function of a salt bridge is in order to maintain electrical neutrality in both of the half cells. If electrical neutrality is disturbed and there's too much of a build-up of charge in either of the half cells, the reaction will run to its equilibrium far too quickly and our battery goes flat very, very quickly. So how does this work? So in this salt bridge, we've got sodium sulfate, right? So we've got sodium ions and sulfate ions. So there you see, we've got our ions. Now when the zinc was oxidized and moved into the solution, we had a buildup of positive charge because there are now more positive ions in the solution. So the buildup of positive charge attracts the negative sulfate ion, and the sulfate ions move into that solution and it re-establishes the neutrality in that half cell. On the other side, copper positive ions moved onto the electrode. So there were now fewer positives in that half cell, which means there was a buildup of negative charge. That buildup of negative charge attracts the sodium positive ions, and those sodium positive ions then move into that half cell and it re-establishes the neutrality. So everything that influences rate of reaction is going to influence the EMF of our cell. So if we have an increase in concentration, the reactions happen more quickly and we get more electricity, right? If we increase the temperature, again, things happen more quickly, more electricity, and sometimes we use gases as electrodes, and in that case, the pressure of the gas is also going to affect the rate of the reaction. So how are we going to compare different galvanic cells in order to say, yes, this is a better material to use in our cells than this. We get more electricity when we use this, etc. When different temperatures and different concentrations and pressures is going to influence our readings. So what we do is we use standard conditions so that we can make comparisons. So our standard conditions are concentration of 1 mole per decimeter cubed. We have pressure at 1 atmosphere or 101.3 kilopascals, and we have temperature at 25 degrees Celsius. So because we have cells that are under standard conditions, right, we can now make comparisons. And we make comparisons by using the table of standard reduction potential. But if we want to compare how good one thing is at being reduced or oxidized, we need something else that is going to participate in the reaction. So what we did is we chose a benchmark. We said this is going to be the one half reaction that we compare all the other half reactions to. And that one there is the standard reference electrode. It's when we put hydrogen gas in a tube around a platinum electrode, where the hydrogen gas is going to be either oxidized or reduced depending on what it's reacting with. So we said that's the benchmark, and we're going to call that 0.00. And everything else we hooked up with it, and we compared it to the hydrogen to see, is it better at being oxidized or reduced, and what is the EMF we get from this under standard conditions. So we can then use this table in order to find the voltage of our cell under standard conditions. And what we do is we go to the table and we go and see what is being reduced, because that's at the cathode, and we substitute it in there, and we see what is being oxidized, and we substitute it in there for the anode, and the answer we get is the EMF of our cell. So if we have a positive EMF, it means we had a spontaneous reaction, and if we had a negative EMF, then something went wrong because we don't have a spontaneous reaction, and we need spontaneous reactions in order to have galvanic cells. But remember, we can only use this under standard conditions. Let's talk about cell notation. So cell notation is just the story of what happened in the cell. It's a little summary. So I want to talk about the anode first. So remember, oxidation happens at the anode. So we're just going to write the story of how oxidation happened at this anode. So we had chlorine ions that were in the solution that lost its electrons, because oxidation is lost, in order to form chlorine gas. At the cathode, we're just going to tell the story of reduction. So we had copper ions in the solution, and those copper ions gained electrons in order to form solid copper on the electrode. Right, so a convention here is that we always write the anode first and the cathode second. But you already know to do that because you know your ABCs. A comes first in the alphabet, so the anode comes first. The only exception is when we're writing cell notation that includes the standard reference electrode, and there the convention is to write the standard reference electrode first. Right, then there's the one slight complication of what if we used electrodes that don't participate in the reaction. So if that happens, we have to write those electrodes in on our cell notation. So if the anode was an electrode that didn't participate in the reaction, we're going to write it there on the far left. And if the cathode was an electrode that didn't participate in the reaction, we put it out there on the far right. So in this particular reaction, we had carbon that was the electrodes, and as a result, the chlorine and the copper didn't form part of the electrodes, but it would kind of have looked like the copper solid did because this copper plated onto that electrode. Right, so that is our little tale of galvanic cells. Hopefully you would have learned a lot about that, and my advice to you is to just practice.